You type a command, or you trigger a deployment pipeline, or you click a button in a console. Somewhere in that action, a request leaves your machine, or your CI system, or your browser, and travels to a cloud API endpoint. The API receives it, validates it, returns an acknowledgement. The whole round trip takes under a second. And then something happens that you have never seen. Your request enters a system that has no status page, no queue depth metric, no estimated wait time, no position indicator. A system that is simultaneously processing requests from millions of other customers across dozens of regions, making decisions about physical hardware that exists in buildings you've never visited, managed by teams you'll never meet, under constraints you'll never be told about. What happens in that system, between the moment your request arrives and the moment your resource appears, determines how long your provisioning takes. It varies by a factor of 10 on the same resource type, on the same day, in the same region, for reasons that are invisible from the outside. This video is a journey into that system, what's actually in there, how it decides what to do with your request, and why trusting it to be fast is one of the quieter fragilities in modern cloud architecture. Your request arrives at the control plane, the management layer that handles all API calls for a given service in a given region. The control plane's first job is validation. Is this a well-formed request? Does the account have permission to make it? Does the requested configuration actually exist? Is the AMI ID valid? Is the subnet in the right VPC? Is the instance type available in this availability zone? These checks are fast. They run against data the control plane already has in memory or in a nearby cache. If validation fails, you get an error immediately. This is the good outcome: fast, clear, actionable. If validation passes, the control plane does something that is almost completely invisible to you. It writes your request to a durable queue and returns the 200. This is the moment the confirmation arrives at your terminal, and at this moment, your resource does not exist. Nothing has happened on any physical hardware. The only thing that exists is a record of your intent, sitting in a queue, waiting to be processed by a scheduler that is handling every other provisioning request in this region simultaneously. The queue is not empty. It is never empty. The question, the one that determines your provisioning latency, is how deep in the queue your request lands and how fast the scheduler is moving through it right now. The scheduler's job is to take requests from the queue and find physical capacity to fulfill them. This sounds simple. It is not. The scheduler is managing a finite pool of physical hardware, real servers, in real racks, in real data centers, against a continuous stream of provisioning requests. Each server has a specific CPU architecture, a specific amount of memory, a specific set of storage and network capabilities. Each request specifies an instance type, which maps to a specific set of hardware requirements. The scheduler's job is to match requests to hardware, quickly, efficiently, at a scale that involves millions of decisions per minute across hundreds of thousands of physical machines. The scheduler also has to account for constraints you didn't specify in your request: placement groups, rules about which physical hosts can or can't run certain combinations of workloads, dedicated tenancy, whether the hardware can be shared with other customers, spot versus on-demand versus reserved, which capacity pools the request is eligible to draw from, availability zone balance, whether the region is trying to spread load evenly across its physical locations. And underneath all of this is the fundamental constraint: physical capacity is finite. If the hardware that matches your request's requirements is currently fully utilized, every server that could run your instance type is already running someone else's workload. The scheduler waits. It checks again. It may look at adjacent capacity pools, different hardware generations that are compatible with your instance type. It may wait for capacity to free up as other customers' instances terminate. This waiting is provisioning latency, not network latency, not API overhead. Physical capacity search time, the scheduler working through its options until it finds hardware that can accept your request. On a quiet Tuesday morning, this takes 15 seconds. During a regional traffic spike, during a major re:Invent launch when everyone runs the same demo, during a disaster recovery event when an entire availability zone's worth of customers simultaneously try to provision replacement capacity, it can take 8 minutes or 20. or it can fail with insufficient capacity after waiting long enough that the control plane gives up. From your terminal, all of these scenarios look identical until they resolve. The command runs, the cursor blinks, you wait. The scheduler has found a physical host. Now the work of actually creating your resource begins, and this is the stage most engineers have the most intuition about, even if they've never thought about it explicitly. For a virtual machine, the hypervisor on the selected host receives an instruction to create a new VM. It allocates a slice of the host's CPU time, carves out the requested amount of memory, maps virtual disk storage to physical block devices, creates virtual network interfaces, and connects them to the physical network fabric. None of these operations are instantaneous. The memory allocation requires zeroing out the allocated pages, a security requirement, so one tenant's data doesn't appear in another tenant's new instance. The virtual network interface creation requires coordination with the network control plane to assign IP addresses, configure routing, update the SDN fabric. If you're booting from an AMI, the root volume needs to be populated. For smaller AMIs, this is fast. For large AMIs, multi-gigabyte machine learning environments, pre-configured software appliances, the data transfer takes measurable time. Then the OS boots. For Linux instances with minimal user data, this is fast. For instances with complex user data scripts, package installations, configuration management runs, service initialization, the boot process can take several minutes. All of this happens before the instance reaches running state, before it appears in your console, before the status checks pass. And status checks are themselves a source of latency that's easy to overlook. AWS runs 2 status checks on every instance, a system status check that verifies the underlying host is healthy, and an instance status check that verifies the OS is responding. These checks run on a polling interval. An instance that becomes healthy between 2 checks will wait until the next check interval before that health is recorded. Add that polling delay to everything else, and the total time from API call to 2 checks passed is substantially longer than the time from API call to the instance actually being ready. Here is the operational consequence of understanding this journey. Provisioning latency is not a constant. It is a variable with a distribution, a range of possible values, with a mean and a tail that extends much further than most engineers build for. If your deployment pipeline assumes provisioning takes 2 minutes, and today it takes 12, your pipeline times out. Your deployment fails. Your on-call engineer gets paged at 3 a.m. to diagnose a failure whose root cause is that the cloud's scheduler was busy. Not a bug, not a misconfiguration, just a queue that was longer than your timeout assumed. If your auto-scaling policy triggers new instances during a traffic spike and assumes those instances will be serving traffic within 3 minutes, but the spike has also stressed the provisioning infrastructure and instances are taking 7 minutes to become ready, your scaling is not keeping pace with your load. The scale-out event that was supposed to protect your system is instead racing against the degradation it was meant to prevent. If your disaster recovery plan requires spinning up a replacement environment in a different region within a 15-minute RTO, and you test that plan on a quiet Wednesday afternoon when provisioning is fast, but execute it during a major incident when every team in your company is simultaneously trying to provision infrastructure, your RTO is based on data that doesn't represent the conditions under which you'll actually need it. In all 3 cases, the dependency isn't on provisioning being fast, it's on provisioning being predictably fast, a property the system never promised and cannot guarantee. The engineers who design around this don't try to make provisioning faster. They build systems that are resilient to provisioning being slow, longer timeouts with explicit handling for timeout cases, auto-scaling that triggers earlier before the system is already degraded, disaster recovery plans tested under load, not on quiet afternoons. None of these are complicated. All of them require knowing that the queue exists and that its length is not your problem to solve, only your problem to account for. Between your API call and your resource appearing, there is a journey you've never seen. A control plane that validates and queues. A scheduler that searches for physical capacity against constraints you didn't specify and can't inspect. A host that allocates, zeros memory, creates virtual hardware, and coordinates across multiple control planes simultaneously. An OS that boots, runs your scripts, passes health checks on a polling interval. Every step takes time. The total time varies with factors that have nothing to do with your request: the load on the scheduler, the availability of matching hardware, the size of your AMI, the complexity of your user data, the interval between status check polls. You cannot see the queue. You cannot query its length. You cannot know how long your position in it will take to reach the front. What you can know is that it's there, that it's variable, and that any system you build that depends on it being short is a system with a fragility you haven't yet discovered. The queue doesn't announce itself, it just makes you wait. And sometimes, at the worst possible moment, it makes you wait much longer than you planned for.